Hey everybody, welcome back. Mr. G here. Today we're going to talk about an introduction into the AC waveform, so the sinusoidal waveform. Where you can get some extra information, chapter 11 of our textbook, Principles of Electric Circuits, Conventional Current Flow from Floyd and Buckla. Again, we are using the 10th edition. So chapter 11 is basically the introduction into the AC waveform. So before we get started, what is an AC waveform and how does it differ from the DC waveform that we've been talking about since the beginning of class? Well, here's what we've got. We have a DC waveform. So DC, as we all know, stands for direct current. What does that mean? Well, direct current means at any given time, the current is only flowing through one direction of that circuit. So if I took a simple little circuit like this, with a DC supply, this side of the supply is always positive. So we know that conventional current flow says that current will flow from the positive side to the negative side. So it flows through the circuit in this direction, so from positive to negative. So direct current, or DC, means that the voltage causes current to flow from the positive side to the negative side. That current will not change direction, it will always flow this way. On the other side, we have AC. Alternating current. With an AC waveform, it is a sinusoidal waveform. I'll put it on the same two resistors. The waveform itself actually looks like this. Where this is our point of reference at 0, this is a positive voltage, this is a negative voltage. What that means is that current that is flowing when this sine wave is positive is going in one direction. Now the value will grow and shrink as the waveform does, but it all flows in one direction. So for this positive section here, we'll say that that red line there is the direction of current. Then what happens is the waveform crosses the 0 point and goes negative. Now, in electricity, negative doesn't mean a small value. So it doesn't mean that -3 is smaller than -2. So in electric circuits, and we're talking about current, voltage, what negative refers to is direction. So opposite direction. So when something is positive, it's in one direction. When something is negative, it's in another direction. So the negative side, we'll make this in blue. The negative side, for the length of that part of the waveform, the current actually changes direction and flows opposite. So in this positive part of the waveform, the current is flowing in this direction. The negative side of this waveform, the current is flowing in this direction. So again, negative doesn't mean smaller in electricity. Negative has to do with direction. So this waveform is what we're talking about when we're looking at AC. So we're going to leave the DC for a moment, and we're going to come into the realm and introduce you to the AC waveform. So the AC waveform has many components to it. So if I was just to draw a waveform, so a sinusoidal type waveform, like so. There are many parts to this waveform, but before we start looking at all these parts, what these values mean and so forth, I think what we need to do is we need to figure out how this thing is created. We know DC comes from a battery type supply. So we have a positive side of a battery and we have a negative side of the battery. Current in conventional current flow will flow from positive to negative. It's very simple. But what we have in an AC waveform is something completely different. We have to generate this type of waveform, and that's where it comes from. It comes from a generator, so an electrical generator. So an electrical generator by definition is a machine that converts mechanical type energy into electrical energy. So something has to cause the machine to spin, creating voltage or current coming out the other side, so electrical energy. So how does that actually work? Well, let's take a look at a real simple generator. So a real simple generator is made up of a couple of parts. There is what we call the stator. In the stator there are some windings of wire. Inside the basic generator we have ourselves a magnet. The magnet is allowed to rotate. So we will call that the rotor. So the rotor actually rotates around inside the stator. So what I'm going to do is I am going to label up here, this is going to be A, and this is going to be end B. So at this point, we don't care about what's making this rotor spin. Okay, we're only caring about what's coming out of the generator. But what's actually the mechanical input? At this point, we don't care. So it could be a gas generator, it could be a turbine on top of a windmill, it could be something like the big turbines that they have at Niagara Falls. It doesn't really matter. So for this particular case, we're going to say that this thing is actually being spun by Superman. So Superman, when he's not solving crimes, preventing world disasters, Superman spends the rest of his time spinning the generator. Make sense? Does to me. So what happens is there's a crank on the side of the generator and Superman comes along and he starts to spin the generator. And what that happens is inside the generator it causes this rotor to go around. Now this rotor is a permanent magnet. We've got a north and a south side. Okay, so a north and a south side. And as this basically spins all the way around, it causes an effect inside the generator. So what does that effect look like? Well, inside this wire, and inside this wire that's making up these little windings here, there's electrons. The electrons are negatively charged. The electrons actually have a reaction to a magnet. So let's just say that the electrons are attracted to one end of the magnet and they are scared and run away from the other end of the magnet. So when I spin this, or Superman spins this, as these poles of the magnet are coming close to and then away from each of these windings, it's causing a reaction to the electrons. It's causing the electrons to either run to the magnet or run away from the magnet. Okay? So, what's happening as Superman is spinning this, as this, we'll call it the North Pole, as this North Pole is approaching here, the electrons in that wire are running from the wire and running towards the magnet. When the magnet gets here, at its closest point, it will have the largest magnetic field effect on that wire. So that causes the most electrons to move. As the rotor spins away, the magnetic field dies off. So, again, as we're approaching, the magnetic field is starting to have an effect on that wire. Electrons are starting to come there, come there, come there, and then it starts to die off. Once we get down to this point, that end of the magnet is going to start attracting electrons from the other side. So now instead of electrons coming this way, electrons are coming this way. They are going in the opposite direction. So as we spin this around like so, we're building up electrons over here, then they're dying off, then we're building them up over here, then they're dying off, and they're building them up over here, dying off, etc., etc., etc. And as we go around, we are actually causing electrons to move in one direction and then electrons to move in the opposite direction. So as Superman spins this around, the electrons in those wires are actually moving. So what we would do is we would end up taking out of this generator some wires, putting that off to the circuit, and we end up with a waveform that's being generated from this spinning of this magnet inside the stator. So what does that actually look like? Well, here is our waveform. This is the sinusoidal waveform. And I'm going to try and put as much of this onto the screen at the same time as I can. Here we go. So, when the rotor ends are as far away or equal distance from each of these little windings, as that happens, the value of voltage that is created or movement of electrons is zero. Because what happens is this end of the magnet is trying to get electrons to go this way, this end of the magnet is trying to get electrons to go that way. Since they're both equal distance, they cancel each other out. Same thing here. So at this moment in time, when the magnet is at this position, right here, no voltage or current is being created. So what happens is, as Superman starts to spin this, as this magnetic field comes up, electrons are starting to build in that particular winding. So basically coming up, 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 until we get to the closest point from where this magnet is closest to that set of windings. We are now at the peak. So the magnet is having the greatest effect, moving the most electrons at that moment in time. Then as Superman continues to spin this thing, it goes all the way down, and the electrons start to fall off as this moves away. And then when we get back to this position here, we're crossing zero. Now, that end of the magnet, which was causing electrons to be attracted over here, is now coming to the other side. So now the other side is actually attracting the electrons. So the other side is attracting the electrons to here, and as we are coming along, we are building up, building up, building up, until we get to here. Again, it's the greatest point of attraction, so it's causing the greatest effect. It just happens to be in the opposite direction from this one. Doesn't mean it's smaller, it just means it's in the opposite direction. And as Superman actually continues, and we end up coming back to where we were right here. Okay, so that completes one full rotation of our generator, completing one complete sine wave. So if we looked at it, we call this 0. So that's our start. The rotor moves 90 degrees. We are here at the peak, 90 degrees. So that's the positive maximum value. We now have the rotor move all the way here, which is 180 degrees, is where it crosses 0 again. And then we go here, and this is 270 degrees, and 270 degrees, we are at the negative peak value, the negative maximum value. And then we continue around to here, and we end up with 360 degrees of rotation. So one waveform is actually divided up into angular measurements, and it can be look like 360 degrees of rotation. So one rotation is one waveform. So what we have is one rotation giving us one waveform. So that's this one waveform here. We have 0, 90, 180, 270, and 360 degrees of rotation, giving us one complete waveform. All right, we're going to bring back this generator. There's our generator. Now Superman comes in and he's going to spin the generator. It takes a certain amount of time for Superman to actually spin the generator around and around. So how much time does it take for the generator to move in 360 degrees? So for one rotation, how much time does it take? When we look at that, one rotation is actually a measurement of time from here to here. This is known as the period of the waveform. And the period is actually a measurement in seconds. So how much time does it take for this rotor to go around one time? So from this point to this point, how much time? That is what's known as the period, and it's a measurement of seconds. Then Superman goes and starts spinning this thing over and over and over again. How many times does he spin the generator in 1 second? That is a measurement of the frequency. So how many times in 1 second does this generator go around? That is a measurement of frequency. That frequency, the unit, is the hertz. So frequency is actually times around, or periods per second. So you can actually take a measurement of 1 over the period is how many cycles or how many times around it actually goes in 1 second. So frequency is equal to 1 over the period, or period is equal to 1 over the frequency. So you've heard many things like, oh, our voltage is running at 60 hertz. So that means that we have 60 of these waveforms being generated inside a generator every second. So that means that Superman is spinning this 60 times a second. So that takes care of the time measurements. whether it be the length of time for one complete cycle of this waveform, known as the period, or how many of those are happening in 1 second, that is the frequency. There are some other important things that we need to know. Like, what is the value up here when it reaches this top point? This is what's known as the peak value. And because it's on the positive side, it is known as the positive peak. Here, we have reached the peak value, but it is now the negative peak because it's on the negative side. Again, negative doesn't mean it's smaller. Negative just means that it's moving in the opposite direction. So we have the positive peak and we have the negative peak. There are a few other things that we need to look at. A measurement of value from this point to this point. So from the positive peak all the way to the negative peak. This is known as the peak-to-peak measurement. So it's taken from the positive peak all the way down to the negative peak. There are two other measurements that are important in our AC waveform. One is what's known as the average. If you actually took the average of this waveform, it would be 0. Because we have the same amount going positive as we do going negative. But the average in this waveform is actually only taken from the bottom side, or one side of the waveform. So either the top side or the bottom side. So we're looking at just one half of the waveform gives us the average. The average value is actually 0.637 times the peak value. That will give us the average of that particular waveform. The next is probably the most important, which is called the RMS value. So the RMS value is 0.707 of the peak value. So whatever the peak value is, multiply by 0.707 and you get the RMS value. So what does RMS actually mean? Alright, so again, what does that RMS actually mean? So, RMS. Well, what it stands for is root mean squared. It's a formula. So if you take 1 volt of peak value and you square it, take the average or the mean, and then the root, you will actually get 0.707. So that's where that 0.707 actually comes from. So RMS, the RMS value of a waveform is equal to 0.707 times the peak value. And that's what RMS actually stands for, RMS. But what does it actually mean? So, what does it mean? Well, sometimes RMS is referred to as the effective voltage. So, what does that mean? Well, if I was to take an AC waveform and put it into a light bulb, let's say this is a 40-watt light bulb. If I want to actually compare that to a DC circuit on the same light bulb, so if I want 40-watt light bulb to get a certain brilliance of that light bulb, and I want the exact same brilliance coming out of this light bulb in the DC world. Okay, so going from AC into DC. How do I do it? Well, let's say that this light bulb is 120 volts is the power supply for that light bulb. What I need to do to get the same brilliance is I need to have a voltage here of 120 volts of RMS. So RMS is the equal power point. So it puts the same power on both light bulbs, DC to AC. Now, if I actually figure this out mathematically, if that was my AC waveform and this is my RMS value, so 0.707 times the peak. So if that's my RMS value, my actual peak value is quite a bit higher. So there's the peak value. So the actual peak value of the RMS waveform for 120 volts is approximately 169.7 volts. The RMS times 0.707 is going to give me approximately 120 volts. So if we take a peak value of 169.7 volts, and then we're going to multiply that by 0.707, so let's take here 169 point, here we go, 169.7 volts times 0.707 is going to give us 120 volts. So what this says is that to compare AC and DC when it comes to putting out the same power, we must use the RMS value of the AC waveform to be the same as the value of DC. So 120 volts of RMS, which actually is 169.7 of peak, 120 volts of RMS is equal power to 120 volts of DC. So that means light bulbs will give off the same brilliance. Resistors will give off the same heat. So it has to do with power. Equal power points. Between AC and DC. That's what RMS is. So, if we look at our waveform once again, we have our 360-degree rotation of our generator. We have peak values. We have minus peak values. We have peak to peak values. We have a period, which is the amount of time it takes to go through one rotation of the generator, therefore one waveform, or the frequency, how many happen in 1 second. We also have a measurement of average value, and the most important one is RMS value. So again, RMS value is that equal power point between AC and DC. That is the one that we see most often. When you look at the electrical plugs in our houses here in Canada, so we take a look at the electrical plug. Here we go, fancy plug. This plug is 120 volts RMS at 60 hertz. That is what's being sent to us from your hydro supplier here in Canada. So 120 volts, that's an RMS value. 60 hertz is the frequency of that waveform. So that is the introduction into the AC waveform. If you want some more information, you can go to chapter 11, again, of our textbook, Principles of Electric Circuits, Conventional Current Flow, Floyd and Bucklaw. you can go to chapter 11 and take a look, and there will be more information there on the AC waveform. So, I hope that helps. Everybody take care, and we'll see you again next time.